Hi, welcome to Physics Teacher, the channel that prepares you for the Waterloo Math and Science contests. This is a grade 9 Fryer contest question. It's the last question from the year 2021. And in it, we have an SF path that starts at S and follows along the edges of the square and ends at F. And you have to be careful never to visit any vertex more than once. A vertex is where two or more of the square edges meet. Now there's three parts, culminating in part C, that says if we have this diagram below, how many possible paths are there from S to F? Give it a try, and I'll be right back with the solution. Alright, so we're going to start with part A, which says to draw the SF path that passes through each vertex except for X and Y. So if we want to pass through every vertex, we'll start by going up, over. So you can see this is a vertex, this is a vertex. Where we start is a vertex. Here's a vertex. And then we're going to continue to go over. We can't go up. So we continue like so, hitting every single vertex. So that's the path we would need to take. Next, we'll move on to part B, which says explain why no SF path exists through all vertexes C, A, and B in this diagram. Alright, well let's start at S. Now, if we go to the right, then there is no way we can go through the vertex C. You could go up and left, but at this point, you're stuck because remember our rule, we can never visit any vertex more than once. So that means if we're going to go through C, we have to go up. And at this point, we have to go right, and we get to this point here. Alright, so here we have three options. We can go up, right, or down. Now, if we go down, then we can go through vertex B, but notice there is no way to get to vertex A and then back to F without visiting more than one vertex. We can't go left here, so we would have to go up and then over to A, and then we're stuck. We can't get to F. Now there is another way to get to B, and that is to continue going right and then down, but then again we're stuck. So let's try go to A first then. To get to A, we can either go right and then up and over to A, but that leaves us stuck once again. So we're only left with one option, to go up. Now from here, is there a way to get to B and then to F without passing through the same vertex more than once? Well, we'd have to go right. And if we wanted to get to B, we'd have to go down, and then you can see there's no way to get to B and then back to F without crossing the same vertex twice. So this is impossible. Finally, our last question, C. Determine the total number of paths from S to F in this diagram here. So in this diagram, we're going to split it up into three parts. So let me draw some lines here. So this middle part looks very similar to part B, and the two ends look similar to part A, except that each end is a total of 18 squares long. And that's the same for, let's call this part 1, part 2, and part 3. So part 3 is also 18 squares long, because we have these two squares and these two squares, which add up to our 20. So let's first analyze that first part. And in our first part, we're going to end up either at this vertex or this vertex. Now there's lots of ways to do that, but as we go through each square, we have two choices really. We can either go through the top portion of the square or the bottom portion of the square. You can't go through both, and here's why. If I were to start at S and move right, the only way then to get through the top part of the square would then be to go up and left, and then I'm stuck because I cannot get back to where I was without crossing a vertex more than once. So that means you can only go through either the top portion, or the bottom portion. So one option would be to go top, bottom, bottom, and so on, and maybe end up here. You can have different examples where you might end up here, but either way, for each 18 squares, you have 2 options. That means we have a total number of 2 to the power of 18 paths. Now this is the exact same for the third portion. In the third portion, if we start either here or here, we can end up at F by, again, through each 18 squares, a total number of 2 to the 18 paths in order to accomplish that. So if we combine 1 and 3, that's a total of 2 to the power of, we multiply them. When we do that, we add their exponents. So 2 to the power of 18 times 2 to the power of 18 will equal 2 to the power of 36. All right, now we're going to look at path 2. So let me redraw path 2 here a little bit bigger. And let's label these vertex points. The incoming and outgoing vertex points is here, here. So these are where the possible paths of 1 can end. And here's the possible paths of where our third portion can start. So let's call them Q, R, and T and U. So what this means is we have a couple options. Either path 1 ends at R, and we can go from R to T, or we can end at R and move to U, or we can end at Q and move to T. Let's call that QT. Or we can end at Q and move to U. So QU. All right, let's start with RT. How many possible ways is it to go from R over to T? So our first path, we could go all the way to the right, up, and then over. So that's one possible option. Another possible option would be to simply go up and over. And a third possible option would be to go down, up, and over like so. So these 3 options would be to get from R to T without going through Q or U. So there's 3 possible options here, or 3 pathways. Now let's look at RU. How many ways are there to go from R to U without going through Q or T? Well, the first one would be to go straight across. A second one would be to go up at this point, and then down and over to U. And our third option would be to go down instead of up, and then over to U. So again, going from R to U, we have 3 possible pathways. Now let's see how many pathways there are to go from Q to T without going through R and U. So our first one, we can go all the way over, up, and over. So there's one pathway. Let's try another. We could go over here, up, and over. So there's a second pathway. See if there's another. Could go over, up, over, up, and over. So there's 3 pathways. Is there any more? Can you find a fourth? There actually is a fourth if we go up and then backtrack. We can backtrack in this case because we're not going through the same vertex twice. So we have 4 pathways to go from Q to T. Finally, let's look at how many pathways there are to go from Q to U without passing through R or T. So our first one would be probably the simplest one. There's one pathway. Next, we could go up here. And then finally, the longest pathway would be to go up all the way over and back down. And that's all the pathways you can take. So there are 3 possible pathways to go from Q to U. Now what this means is, at this middle section 2, we have a total number of 3, 3, 4, 3, or 13 different ways we can get through this middle section here at 2. Which means the total number of different pathways we can take to go all the way from S to F would be multiplying the pathways between each of our sections here, which we have through 1 and 3 and through 2, gives us a total number of 13 times 2 to the 36 pathways.